Okay, we are discussing about the operator method of solving the non-homogeneous differential equation. We are solving only the particular solution using this operator method. When the differential equation is represented in this way, in this equation, where f of d operating on y is equal to f of x, where f of d is the polynomial function of d. Now, there are different techniques which are used in this operator method to solve this particular solution of the non-homogeneous differential equation. And these are method of successive integration, partial fraction, series expansion. Now we will discuss the first technique, which is the method of successive integration. So the first technique which is used and in this operator method is the method of successive integration. So here in this technique, actually the function is integrated successively. So we know the differential equation is f of d equal to f of x. So here this polynomial function of f of d is written in this way. F of d is equal to d minus r1 into d minus r2 and so on. When this polynomial function is factored in n different terms, where r1, r2, rn are the roots of the auxiliary equation, which is f of d equal to 0. Now we can write this equation as y equal to 1 by d minus r1 to d minus r2 to d minus rn operating on f of x. So so this term can be represented as 1 by d minus r1 into 1 by d minus r2 and up to 1 by d minus rn if there are n factors operating on f of x. So if it is a second order differential equation, then it would have the two roots. So it can be written as d minus r1 1 by d minus r2 operating on fx for a second order differential equation. So here this function is integrated successively, first by this operator and then this operator d minus r1, sorry, 1 by d minus r1. So let me repeat again that successive integration method. Here the function f of x is integrated successively. So for second order differential equation, it would have two parts, that is 1 by d minus r1 into 1 by d minus r2. So the function is first integrated using this operator 1 by d minus r2 and then integrated using this operator 1 by d minus r1. So this is the successive integration. So so we know that 1 by d minus r2 which is this formula e to the power rx into integration e to the power minus rx f of dx. Similarly for 1 by d minus r1 we can write this formula. So this is the method of successive integration. Now uh, let us see some example. Suppose where we can apply this technique. Suppose the differential equation, you have to solve the particular solution of this differential equation y double dash plus sorry, this is minus 3y dash plus 2y equal to x e to the power x. So this is the differential equation, second order differential equation, and we have to solve the particular solution of this differential equation using this successive integration technique in this operator method. Now in operator form, this differential equation can be written as this is d square minus 3d and plus 2 operating on y is equal to x e to the power x. Now so here this is the polynomial function which is f of d. So this can be factored in two terms because uh, uh, so here d square minus 3d plus 2 is can be written as d minus 1 2 into d minus 1. So it is factored into two terms, d minus 2 into d minus 1. So we can write that y equal to 1 by d minus 2 and into 1 by d minus 1 operating on the function f of x, which is x e to the power x. So this is the technique. So now we have to apply the formula. So first first we have to apply the formula for this operator 1 by d minus 1, keeping this term fixed. Suppose this term 1 by d minus 2, this operator is fixed. Now we have to uh, write the integration form of this operator. So this is so here d minus 1, here r is equal to 1, so we can write e to the power x integration e to the power minus x and x into e to the power x in dx. So here in this formula you see, so here r equal to 1, so r equal to 1, that means e to the power x integration e to the power minus x f of x dx. So we get that 1 by d minus 2 e to the power x, so this is simply x dx, and we can write e to the power x here, the operator d minus 2, and this is x square by 2. So similarly we have to write the integral form of this operator. So this is it into e to the power 2x integration e to the power minus 2x, and then x square e to the power x, and this is dx. So so the e to the power 2x by 2 equal to e to the power minus x into x square dx. So this is the simple integration integration of the two products, that is e to the power minus x and x square. I am not calculating this integration, this is simple. So so this is the technique, successive integration. That is you have to integrate this function successively. Now the second technique which is used in this operator method is the partial fraction. So method of partial fraction. partial fraction method. So here partial fraction method means the operator, we know the differential equation in the operator format, f of d operating on y equal to f of x. So so here this polynomial term of this operator d, when it is factored into different terms, these are this function is decomposed into partial fractions. Suppose the polynomial functions of d is written in this way: d minus 1, d minus r2 into d minus r3, and so on, d minus rn up to rn. In the rn, that means it is for nth order differential equation. So uh, so we can write this. So that is y equal to 1 by d minus r1, d minus r2, so on, operating on f of x. So here this term is actually written in terms of partial fractions. That is, y can be written as a by d minus r1, sorry, this is a1, plus a2 by d minus r2, plus a3 by d minus r3, plus up to nth term. I'm not writing the nth term, operating on f of x. So these are the partial fractions. When this polynomial function is decomposed in this way, that is in the partial fractions, then we can uh, easily find out the particular solution or yp of this non-homogeneous differential equation. Now for second order differential equation, then we can write a equal to a1 by d minus r1 plus a2 by d minus r2. This is operating on f of x, because for second order differential equation it has only two terms, d minus r1 into d minus r2, two fractions. This is for second order differential equation. Now let us see the last example which I explained in the successive integration method, that is d square minus 3d plus 2 operating on y is equal to x e to the power x. So taking the same differential equation, which is which is y double dash minus 3y dash plus 2y equal to x e to the power x. So this is written as in the operator form, which is d square minus 3d plus 2 operating on y is equal to x e to the power x. So which is d minus 2 into d minus 1 operating on y is equal to x e to the power x. So now that is y equal to 1 by d minus 2 into d minus 1 operating on x e to the power x. So here this this term actually can be written in partial fractions. 1 by d minus 2 d minus 1 is equal to we can write 1 by d minus 1 minus 1 by d minus 2. D minus no, D minus 2, sorry, this is, it would be D minus 2 and this is D minus 1. So it can be written in this partial fractions. So 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 we can write that y equal to 1 by d minus 2 and minus 1 by d minus 1 operating on x e to the power x. So we get y equal to 1 by d minus 2 operating on x e to the power x, and then for this operator 1 by d minus 1 operating on x to the power x. So this is x e to the power 2x e to the power minus of 2x x e to the power x dx and minus e to the power x integration e to the power minus x and x e to the power x dx. So this is the simple integration, and you will see the same result you will get for this method, this technique also. So the first technique was the successive integration, and then this is the partial fraction method. Next we will discuss about the series expansion method. Next technique in this operator method is the series expansion of operator method. So this in series expansion method, the function is actually written in series. So let me write the differential equation in operator form again. F of d operating on y equal to f of x. So here so y equal to 1 by f of d operating on f of x. So here 1 by d 1 by f of d is expanded in series, as can be represented as 1 plus b1d plus b2d square plus here b1 b2 are constants and d is the derivative, that is the ddx, and d square d is the d2 dx2. So now the higher order term of the d, higher power is neglected, because we can say that d to the power k x to the power n is equal to 0 if k greater than n. Example, suppose it is uh, suppose now k equal to 2 and n equal to 1. So that is a double derivative of x, so it is 0 because the first derivative of x is 1, so the double derivative of x is equal to 0. That is why the higher order term is neglected. Now let me so now let us discuss an example. Mm, so suppose the differential equation is y double dash uh, y double dash minus 6y plus 9 equal to x square. So this is the differential equation, and we have to solve the particular solution of this differential equation using the series expansion method of operator. So in operator form we write this is d square minus say, sorry, it is dash 6d plus 9, uh, mm, so this is y plus 9 operating on y is equal to x square. So we can write this d square minus 6d plus 9. So this is can be written as d minus 3 into d minus 3. So it is factored into two terms, d minus 3 into d minus 3. So d minus 3 square, so any one of this. So in series expansion method, actually, so 1 by fd, so here 1 by fd, that means 1 by d minus 3 to the power square, this term is expanded in series. And you see here that the two roots are equal, that is d minus 3 into d minus 3. So this type of problem cannot be solved in using the partial fraction. Now the series expansion method, that means you have to expand binomially this term. So we know the formula for that is the binomial expansion formula. We know that 1 plus minus x to the power n is written as 1 plus minus nx plus n into n minus 1 by 2 x square plus minus n into n minus 1 into n minus 2 by 3 factorial, sorry, this is the 2 factorial, and into x cube plus and so on. So now so here this term d minus 3 to the power minus 2, so can be expanded using this formula. So here you see that x, so now uh, we have to write this term in this way. Suppose it is 1 by d minus 3 square, so taking 3 common, so we can write 3 square, that means d minus 1 square. We can write also this 9, that is 1 minus d, we can write this is same. So now you have to expand this formula, that is 1 by 9, this is 1 minus d to the power minus 2. So here 1 minus d to the power minus 2, so can be written as there is 1. So when it is minus, then it is minus and minus into where n is equal to minus 2. So this is sorry, this is d by 3, and this is 3 by 3. So this is 1 plus and 2d by 3 and plus our n is equal to minus 2 into minus 2 minus 1 by 2 factorial. Her x is d by 3 to the power square, and then we have now since this is the function, this is x square, so d to the power the uh, fourth term is doesn't need it, because you see then it will be a third derivative. So the third order derivative of this x square is 0, so we have to expand up to this term. So now coming to this differential equation, we can write this equal to y equal to 1 by f of t operating on x square. So here f of d, 1 by f of d is this term, so we can write y equal to this is 1 by 9 and 1 plus 2 d by 3. So this is uh, 3 into d square by 9 and operating on x square. So the 1 by 9, 1 plus 2, 3 d of x square plus d square by 3 operating on x square. So 1 by 9, this is sorry, x square. So this is x square plus so derivative of x square, this means 2x, that means 4x by 3 plus double derivative of x square, that means uh, 2 by 3. So this is the particular solution of this differential equation, and using this series expansion technique. Now let us discuss some examples of this operator method. Suppose now this is a question. Examples. Suppose we have to solve this differential equation. Solve the differential equation that is y double dash plus y equal to cosec x. So this differential equation is solved already using the variation of parameter method, and we know the answer, we know the complete solution. So now we have to check the answer solving in this operator method, whether these two solutions are equal or not. Now in this problem we have to find out the complete solution. So a complete solution, so the complete solution is the sum of the general solution of this of the homogeneous differential equation associated with this non-homogeneous differential equation plus yp is the particular solution of this differential equation. Now for solving the homogeneous differential equation of this non-homogeneous differential equation, we write y double dash plus y equal to 0, and suppose y equal to e to the power mx is the trial solution, then we can write that is m square plus 1 into e to the power mx is equal to 0. Here e to the power mx is not equal to 0, then we can write m equal to I equal and minus h. So the values of m are I and minus I. So the general solution is yg is equal to c1 cos x plus c2 sin x. So this problem is solved by the variation of parameter using that formula. So here y1 is the cos x and y2 is the sin x, which are the two independent solutions of this differential equation. Now writing this differential equation in operator form, so we can write it as d square plus 1 operating on y equal to cosec x. So this can be written as d d minus I into d plus I operating on y cosec x. So we write that y equal to 1 by d minus I into d plus I operating on cosec x. So the operator which is 1 by d minus I into d plus I operating on cosec of x. Now here we can use either the successive integration method, or we can use the partial fraction method. So I think the partial fraction method is easy to solve this differential equation. So we can write this as y equal to 1 by 2I. So in partial fraction we can write this as 1 by d minus I and minus 1 by d plus I. So this is the partial fractions of the operator operating on cosec x. So now the y equal to 1 by 2I. So here first 1 by d minus I is operating on cosec x, then minus 1 by d plus I is operating on cosec x. So we can write 1 by 2I. So this is e to the power ix integration e to the power minus ix cosec x dx, and this is e to the power minus ix integration e to the power ix cosec x dx. So this is the equation we get. So now uh, now using this Euler formula we can write 2I, this is e to the power ix, which is cos of x minus I sin x into cosec x dx, minus e to the power minus ix. So this is cos x plus I sin of x into cosec x dx. So now so here the cos x into cosec x, that means cos x by sin x, and minus sin x into cos x, that means it is 1. Sin x into cosec x is 1. So we can write 1 by 2I in e to the power ix, that is cos of x by sin of x minus I uh, integration dx minus e to the power minus x. So this is cos x and cos x by sin x, and this is plus I into dx. So we write that we know the integration of cos x sin cos x by sin x is log of sin x, and so this is simply x. So we can write 1 by 2I integration now e to the power ix, this is log of sin x minus x, and this is e to the power minus ix. So this is log of sin x, sorry, this is ix, and this is plus ix. So taking common log of sin x, you can write e to the power ix minus e to the power minus ix by 2I, and this is, we can write I taking common, so we can write this as x into e to the power ix and plus e to the power minus ix by 2. So the answer is, so log of sin x, this is sin x, and this is cos x, we can write x cos x. So the total solution, so this is the particular solution of this differential equation. So this is the particular solution. We should write it as yp. So the complete solution is given by, complete solution is yg plus yp. So here yg is c1 cos x plus c2 sin x and minus x cos x plus sin x into log of sin x. So this is the solution which we have obtained using the series expansion method in the operator method. So we got the same result in this operator method. Okay. So far we have discussed about this three techniques of calculating the particular solution of this non-homogeneous differential equation. And now we will discuss about some tricks and formulas and the suitable technique of solving the non-homogeneous differential equation depending on the type of this function f. This function f can be either a single function of x or a product of two functions. So depending on this type, we can apply the tricks so that this non-homogeneous differential equation can be calculated, can be solved very easily and without any difficulties. So we will discuss the different types of these functions one by one. Suppose the function okay, suppose the function is a constant. So for a constant function f, we can apply any method among these three techniques, that is the successive integration, partial fraction, series expansion, any method. Now if the function has the form, suppose f of x is equal to x to the power m, or m greater than 0, that means m is a positive integer, so it is either m equal to 1, 2, 3. So the non-homogeneous differential equation is f of d operating on y equal to x to the power m. So we can write here the particular solution of this non-homogeneous differential equation, yp equal to 1 by f of d operating on x to the power m. So for this type of non-homogeneous differential equation, and the function is of the form, suppose x to the power m, then we can apply the series expansion method. So in this series expansion method, this 1 by f of d can be written as a f of d to the power minus 1, and then this polynomial function is expanded in series. So and then just differentiating this function, we can calculate this particular solution. So the useful method, and that is the suitable method for calculating the particular solution of this non-homogeneous differential equation, is the series expansion method. Okay. Now suppose the function f has the exponential term. So in this case, suppose f of x equal to e to the power ax, where a is a positive number. Now if the function is like this, that is an exponential function, then we can write this, and then we can apply this formula, that is let me write first the differential equation, that is f of d applying on y is equal to e to the power x. So the particular solution is yp equal to 1 by f of d operating on e to the power ax. So the polynomial, this f of d is the polynomial function of the operator d. So here the formula is the solution yp is actually 1 by f of d e to the power ax, where this polynomial function of operator d is is written in terms of this constant a. So that is 1 by f of a e to the power ax. So this is the formula. We write as equation 1. So by using this formula 1, we can easily calculate the particular solution yp if the function is a exponential function. So here this polynomial function of the operator d is replaced by the a polynomial function of the constant a. So it is very simple. Suppose the differential equation is, suppose let us discuss an example. Suppose the differential equation is d square minus 3d minus 3d plus 2 operating on y equal to e to the power x. Okay, one thing I should mention that here f of a cannot be equal to 0. To calculate the particular solution using this formula, then here f of a cannot be 0. So if f of a equal to 0, then we cannot apply this formula. Then we have to use the convenient techniques, which are the successive integration or partial fraction method. So for this type of function, you can use the successive integration or partial fraction method to solve this non-homogeneous differential equation if f of a is equal to 0. We know that the derivative of the exponential function is a constant multiplied by this exponential function. That is, if the derivative of e to the power ddx of e to the power ax can be written as a constant a multiplied by the exponential function. Similarly, d square e to the power ax we can write that is a square e to the power ax. So we can write that f of d operating on e to the power ax can be written as f of a equal to e to the power ax. So so here you can see that this polynomial function of the operator d is equivalent to the polynomial function of the constant a. So this is applicable for the inverse operator also. So we can write that 1 by f of d is equal to 1 by f of a. So this is how the formula comes. Now let us discuss an example. Suppose mm, suppose the differential equation is y double dash minus 3y dash plus 2y equal to e to the power x. So this non-homogeneous differential equation can be written as d square minus 3d plus 2 operating on y equal to e to the power x. So the particular solution of this non-homogeneous differential equation is 1 by d square minus 3d plus 2 operating on e to the power x. So here the constant value of the constant, which is the coefficient of x, this is 1. So let me check the value of f of a. So if d equal to 1, then 1 minus 2 plus 2, so which is equal to 0. So we cannot apply this formula here, because here in this case, then f of a is equal to 0. If a, so we cannot apply the formula here. Now let us see another example. Suppose mm, so for this case you have to apply the partial fraction method or the successive integration method. Now let us see another example. Suppose the differential equation d minus 3 to the power square operating on y equal to 2 into e to the power 4x. 2 into e to the power 4x. So here the particular solution can be written as 1 by d minus 3 to the power square 2 into e to the power 4x. So now here let me check that if f of a is equal to 0 or not. So here if we put the value of d equal to 4, then it become that is 4 minus 3 to the power square into 2 e to the power 4x, which is 2 into to the power 4x. So this is the result. So the particular solution of this uh, differential equation this is example 1 and this is example 2 of this differential equation is equal to 2 into e to the power 4x. Now let us see another type of the function f of x. So for exponential function, if f of a is not equal to 0, then we can apply this formula to solve the particular solution of the non-homogeneous differential equation. Now if the function so far we have discussed the function which is a single function of x, that is it is either a constant or a x to the power m or e to the power ax. Now if the function is something like f of x is equal to sine x or sine of ax or sine of cos x, like that, or cos of ax, then can I, so the fourth type of function, if f of x is equal to either sine of ax or cos of ax. So for this type of function you have to convert this sine of ax to the exponential form using the Euler's formula. So we know that sine of x is equal to e to the power ix minus e to the power minus ix by 2i, and cos of x is equal to e to the power ix plus e to the power minus ix by 2. So for this type of function you can apply this the formula 1. So you can use this formula 1 for this type of function, sine of ax or cos of x, provided that if you have to first convert this sine of x to the exponential form. So now we will discuss the type of the function f of x which is a product of two function of x. Suppose if of x is something like this, e to the power ax into b function of x. So for this type of function you can use this formula, which is the formula is so for this type of function, let me write first the differential equation as 1 by f of d operating on y equal to e to the power ax b of ax. So here v of x can be either ax or ax cos ax or x square, whatever. So for this type of function, uh, sorry, or cos x or x square, any type of function, any type of function of x. So so here y equal to 1 by f of d e to the power a of e to the power x into vx. So the formula is written as 1 by f of d operating on it a to the power ax, v of x is equal to e to the power ax 1 by f of d plus a of operating on v of x. So this is called the exponential shift rule. This is equation 2. So we can see the formula 2. It can mm, it is called as the exponential shift formula. So here 1 by f of d is operating on e to the power ax into v of x. Then the exponential term is shifted to the left hand side of this operator, and the operator become the function of d plus a, and this operator then only operates on the function v of x. So if the function is e to the power ax into x, then using this formula we can write e to the power ax 1 by f of d plus a into x. Then simply apply the techniques such as the partial fraction or successive integration method to solve the non-homogeneous differential equation. Now the sixth type of function, suppose if the function f of x has the form that is x to the power m and cos of ax, or x to the power m sine of ax. So for this type of function, again you have to convert this cosine and sine term into the exponential function using the Euler formula, and then you apply this exponential shift formula. So we will not discuss about the proof of this formula. It can be easily proved. So now let us for the product of two functions, and if the function has an exponential term e to the power x, then you can apply this formula to solve the non-homogeneous differential equation very easily. So the series expansion method is applied only for this type of function, so where the differentiation can be easily done and the higher order terms of the derivative of the operator d is neglected. So for this type of function, and the partial fraction method can be applied to any type of these functions, from 1 to 6, that is if f of x is constant, or x to the power m, or e to the power x, or a product of two functions, the partial fraction method can be applied everywhere. But the successive integration has the problem for the function suppose has a form that is a product of two functions. So for product of two functions, the successive integration method has a problem to solve the non-homogeneous differential equation. The successive integration method is useful for a single function of x, but for product of two function, the order of the operation the solution, that is the particular solution of the non-homogeneous differential equation, depends on the order of the operation in the successive integration method. Now let us see the example which is discussed mm, uh, before, that in the successive integration method you see that this differential equation, so y double dash minus 3y dash plus 2y equal to x e to the power x. Here the successive integration method is used to solve the this differential equation, and and you see that here this differential equation is written in this way, that is d square minus 3d plus 2 into y equal to x e to the power x, and d square minus 3d plus 2 is factored into two terms, that is d minus 2 into d minus 1. So here this function f of x is first operated using the operator 1 by d minus 1, and then operated using this operator 1 by d minus 2. Now if the order of this operation is changed, suppose this function is first operated using 1 by d minus 2 and then 1 by d minus 1, then the result will be different. So that is, the particular solution will be different. So here the particular solution depends on this type of on the order of the operation. So this is the problem in this method uh, for solving the non-homogeneous differential equation. So for a product of two function, so the function like this, you can, if the function has an exponential factor, then you can use the exponential shift formula, that is the formula 2, this formula, and so that you can easily calculate the particular solution of this non-homogeneous differential equation. So so far we have discussed uh, about the method of solving the non-homogeneous differential equation and homogeneous differential equation with constant coefficient. So in this mathematical physics course, and it has only the differential equation, that is the homogeneous and non-homogeneous differential equation with constant coefficients only, and we will discuss the homogeneous and non-homogeneous differential equation with non-constant coefficient in the mathematical physics course in third semester.